Today's introduction, Dr. Patricia Pavier. Patricia is the Technical Group Manager of the Radiological Group at the Pacific Northwest National Lab, and she is also the Chair of the Gen 4 International Forum Education and Training Task Force.
Thank you very much, Berta. Good morning, everyone. Very happy to have Dr. Luca Ammirabile from the European Commission Joint Research Center in Petten, the Netherlands, with us today. He is the group leader of the Nuclear Reactor Accident Modelling team of the Nuclear Reactor Safety and Emergency Preparedness Unit. His current research activities are core thermalhydraulic analysis, deterministic code application, and development and safety assessment of advanced reactors. Since 2014, he has been co-chair of the Working Group on Risk and Safety of the Gen 4 International Forum. He is also the European Commission representative of the OECD NEA Working Group on the analysis and management of accidents, and also the Working Group on the Safety of Advanced Reactors. Prior to 2007, when he joined the European Commission, Dr. Ammirabile worked at the Tractebel Engineering in Belgium in the Thermalhydraulics and Severe Accident section in support of the safety assessment of the Belgian Nuclear Power Plants. In 2003, he earned his PhD from the Imperial College of London, and in 1999, he earned his master's degree in nuclear engineering from the University of Pisa, Italy. So without any further delay, I give you the floor, Luca, and I thank you on behalf of the GIF Education and Training Task Force for volunteering to give this webinar. Thank you so much, Luca, and you have the floor.
Thank you, Patricia, and welcome everyone to this webinar on the safety of Generation 4 systems. As you've seen from the summary of this webinar, I'm going to talk about the establishment of the safety approach of Generation 4 systems based on the work done by the Risk and Safety Working Group, which is one of the cross-cutting methodology working group that has been established within GIF. I hope you see the view here. Yes, perfect. So we will start our virtual journey with a recall of the GIF safety goals. I will then shortly speak about the scope and the objectives of the Risk and Safety Working Group before going more into detail of the basic safety approach for Generation 4 reactors. I will also briefly describe the ISAM, the Integrated Safety Assessment methodology that was developed by the group, indeed, to assess the safety of Gen 4 systems, with a very short pilot application of the methodology itself. I will then close this webinar with an overview of the ongoing Risk and Safety Working Group activities. So let's start with the recall of the Generation 4 safety goals. So as you well know, at the beginning of GIF, technology roadmap was drafted where a set of goals were put in place for 4 main domains: sustainability, economics, proliferation resistance and physical protection, and indeed safety and reliability. These goals were put in place literally to stimulate the research for innovative systems and also to somehow motivate and guide the research and development on Generation 4 systems. As for concerns safety and reliability, we have then 3 goals. The first calls for Gen 4 system operation that will excel in safety and reliability, system that will have a very low likelihood and degree of reactor core damage, and finally, Gen 4 system that will eliminate the need for side emergency response. We will shortly see the interpretation of these goals into the safety approach for Generation 4 systems. But a first point that I want to raise is the fact that these goals, as embedded into the Generation 4 International Forum, should be applicable to all 6 Generation 4 systems, despite their very different characteristics. In fact, you can see in this table all the differences that the 6 systems have in terms of, in particular, neutron spectrum, type of coolants, and operational pressure and temperature, as well as differences in reactor size. It's clear then there was somehow a need to have a kind of harmonized approach on safety for Generation 4 systems. And this eventually led in 2004 to the establishment of the Risk and Safety Working Group, which is one of the 3 methodological working groups, cross-cutting working groups of GIF. The RSWG had in particular the objective to promote a consistent approach on safety for Generation 4 systems, define what were the safety principles and objectives based on Generation 4 safety goals, with a clear view to guide somehow safety-related R&D activities, and finally the development of a technology that could be technology neutral, a methodology that could be technology neutral, and that could lead then the assessment, the safety assessment of Generation 4 systems. Let's see now a bit more what are the main aspects of the Generation 4 safety philosophy as developed within the Risk and Safety Working Group. So, first of all, considering that the safety objectives of the so-called Generation 3 evolutionary light water reactors are already very ambitious, there are still margins for further improvement and then for a higher safety level for Generation 4 systems, considering essentially the combination of inherent advanced features due to the innovative technology and, very important, an early application of the safety approach, or a safety philosophy, so that we can achieve a robust design in a way that safety is already from the preconceptual stage built in the design itself rather than added on. In second instance, the Risk and Safety Working Group recognized the utility to base the safety assessment on both the deterministic and probabilistic approach, clearly to the extent and limits of the available experience in potential very innovative technologies. Another point is clearly that the design should address all plant conditions, including severe plant conditions. Design should also take due account of internal and external hazards and should make use as much as feasible of modeling and simulation activities in the design itself. In a summary, all these attributes essentially call for a full implementation of the defense in depth already from the early design stages of Generation 4 systems. And this is somehow in line with the same safety and reliability goals that as well can be somehow summarized for looking for an enhancement of the defense in depth in the design. In fact, when we talk about excellence in operational safety and reliability, Essentially, we are addressing the safety during normal operation and anticipated operational events, focusing really on the reinforcement of level 1 and level 2 of defense in depth. Then when we talk about very low likelihood and degree of reactor core damage, we want to minimize the frequency of the initiating events, introduce specific design features for the control and the mitigation of accidents in order to avoid core damage. So we want to reinforce level 2, level 3, and in general the design for severe accident prevention. Finally, when we talk about eliminating the need for offsite emergency response, we look at a comprehensive safety architecture that is able to manage and mitigate severe plant conditions and also reduce the likelihood of early or large releases. In this respect, we want, once again, to strengthen the 4 level of defense in depth, which is dedicated to the design for severe accident mitigation. So the defense in depth is already a fundamental principle of nuclear safety, and it must be preserved and even reinforced in the design of generation for systems. Indeed, this is the key to achieve the safety robustness that will then lead to enhancement of the safety of generation for designs. In addition, to meet these objectives, the defense in depth should be implemented in a way that is, first instance, exhaustive, so that all the risks that could affect the fundamental safety function should be identified in a comprehensive way. The defense in depth should also be progressive in the sense that accident scenarios should eventually cause a progressive failure of sequential failure of each level of defense in depth, and therefore reducing the likelihood of this to happen without having short sequences or kind of bypass leading directly from level 1 to level 4. Additionally, the defense in depth should be tolerant in the sense that any small deviation of the physical parameters outside the expected range should not lead to severe consequences. Essentially, we should not have any kind of cliff edge effect. Another important aspect is forgiveness. So assure that a sufficient grace period is allowed for manual intervention and repair during accidental situations. And finally, the design and the defense in depth should be balanced in the sense that a specific accident sequence should not contribute in an excessive or unbalanced manner to the global frequency of the damaged plant state. These 5 attributes really reinforce the implementation of the defense in depth. And additionally, I will say we also the design of Gen 4 system should also lead us as far as feasible to a simple design. Take into account that generally simple design assures a higher level of robustness and safety. And this somehow differentiates Gen 4 systems from the high complexity is experienced in particular for Gen 3 systems. I also want to highlight the fact that these attributes were actually defined in the early 2008, but somehow they already answers to the challenges that came after the Fukushima accident. In fact, when we talk about progressiveness of the defense in depth, essentially we want to avoid any short sequence as what happened, for example, for Fukushima, as well as any potential for cliff edge effects when we say about the tolerant implementation of defense in depth. And also in terms of forgiveness, to have enough time to to be able to have manual intervention in case of a potential accident. Let's go now more on the basis for the design and assessment. Clearly, the design of Generation 4 systems should cover the full range of plant states, including severe conditions. And the special attention should be given to severe plant conditions while the implementation of specific provisions that could be put in place against such conditions. Additionally, all internal events and internal and external hazards have to be considered, together with eventual uncertainties that are related to the innovative features of a new technology. And this should be put in place in particular through a combination of both experimental and modeling activity. Finally, a special effort should be made in particular for the demonstration of the practical elimination of all those accident sequences that can be associated with the potential for early or large releases. So looking in particular at the plant states that Generation 4 systems should cover, essentially these go from the normal operation all the way to design extension conditions, while auto design are essentially all the residual risk and practically eliminated accident. I would like to spend some words about the notion of severe accident. In fact, some concepts, some Gen 4 concepts, can clearly associate the notion of severe accident with that of light water reactor associated with the core, the melting of the core. However, designs like the VHDR and the molten salt reactor cannot express potential severe accident conditions through the melting of the core, given their design characteristics. However, this doesn't mean that a severe accident, which is intended as an accident that goes beyond the design basis, cannot be postulated. So in any case, potential sequences that go beyond the design basis needs to be assessed, but it's important to notice that according to the characteristics of some design tracks, the potential severe accident scenario can be put in level 4, so within the design extension, but also can be put also in level 5, so out of the design itself. What is essential aspect in the assessment is that the possible severe accident scenario is indeed considered and evaluated in a global design assessment. So we have seen essentially what are the main principles of the safety approach for Generation 4 system. We see now how somehow we can assess within our design those principles. And this is essentially linked to the development of the ISAM, the Integrated Safety Assessment Methodology, that had the objective to ensure a consistent approach to the safety applied to all 6 systems. The methodology consists of 5 tools. They are not, let's say, new in their formulation. Maybe for exception of the QSR, so the Qualitative Safety Requirement Review, and the Objective Provision 3, or OPT. But actually is really the systematic use of these tools that should somehow ensure the consistency of the design with the safety approach for Generation 4 systems. The set of tools can be used separately, and essentially the methodology covers the full entire cycle from the preconceptual design all the way to the final design, licensing, and operation. I will just shortly introduce each of these tools. starting with the qualitative safety characteristics of safety requirement review, or QSR. This tool is essentially a kind of checklist where in the form of a table, you can see here, in a form of a table, essentially all the safety requirements, safety principles, even guidelines are explicitly mentioned in terms of classes of requirements, from the technology neutral all the way to the design specific, and for the three fundamental safety functions and defense in-depth levels. Based on these tables, any specific design feature, so design characteristics, design system, and so on, can be assessed against the current requirements, the current regulatory framework, to see indeed to which extent this is in line, the system is in line with the current requirements. The second tool is quite well known, is the phenomena identification ranking table. That is a tool quite powerful to identify really the gaps in terms of importance of phenomena, as well a level of knowledge of those phenomena. Indeed, this tool is quite interesting, quite powerful, really to identify any potential R&D needs dedicated to the level of knowledge of important phenomena. Then the third is the objective provision tree. This is a rather qualitative tool that allows to give a graphical representation of the safety architecture. So the set of provisions that are put in place to prevent, to control, and mitigate potential accidents. In addition, identifying essentially the risks or the initiating events, you also put in place all the potential lines of protection against specific mechanisms. So graphically, we have for each level of defense that is specified in terms of specific objectives to be achieved and barriers that need to be protected. And then for the different safety functions, in the OPT, we identify the challenges to cope with and the mechanisms that essentially are the initiating events that need to be prevented or eventually controlled through a set of provisions that can be material in the sense of system features or components, or immaterial in sense of procedures put in place in order to avoid, to prevent or control the mechanism itself. This is a very powerful tool because it allows to have really an overview of the safety architecture, as well as identify really the independence of the different levels of defense in depth, and potentially identify eventually common cause failure that needs to be addressed and can be addressed then in advance. And finally, we have the two remaining tools that are the deterministic phenomenologic analysis, which is the traditional safety analysis that is used to assess the response of the system to the different challenges, and the probabilistic safety analysis that allows to define the risk spectrum on our design, in particular to answer the three basic questions in terms of what can go wrong, how likely is this to happen, and what are the potential consequences. So you can see here that the methodology is really a combination of deterministic and probabilistic. It has this flexibility to enhance one or the other aspect based also on the level of maturity of the methodology itself. So these are the tools. We'll see now how these tools can be applied into the safety assessment itself. To do that, we need to have a kind of, let's say, definition of safety assessment. And this comes from IAEA, from the agency that identify in terms of safety assessment essentially two steps. The first step is the verification of the compliance of our system with what they are the principles, the requirements, and the guidelines of the current regulatory framework. The second step is actually the verification of the conformity of the safety architecture with the expected quantitative safety objectives. So to say, the design criteria that are put in place for each level of defense in depth in terms of characteristic temperatures to achieve in case of accident, or in the later defense in depth level in terms of potential release to the environment. In this table, we have somehow the cross-cutting relationship between the different steps of the design and assessment process with the respective ISAM tools. So in first instance, once the goals, the objectives, principles, so the regulatory framework is put in place and a set of safety options or design options are identified, the first step, as we said before, is to verify the compliance with the current requirements. And this is mainly the work, the domain of the QSR, where this compliance can be verified and eventually a process of identification, correction can be put in place. Once the safety options, the design options are put in place, then the design itself kicks in. So we have in first instance the identification of what are the challenges for the safety functions, as well as identification of mechanisms or the initiating events and plant conditions to be considered in their design. And this is mainly the work that can be performed through PERT exercises together with OPT exercise, take into account that the OPT also identified, also in a qualitative way, the set of provisions that are put in place in order to cope with, to prevent and to control the mechanism. Once this is done, and then somehow the safety architecture is in place, then we have the design and sizing of the provisions themselves and the analysis of the response to the transient, which is the classical, let's say, safety analysis. And this is done through the combination, I would say, of deterministic studies as well as probabilistic studies, with the final assessment of the safety architecture that should be, as I said before, exhaustive, progressive, tolerant, forgiving, and balanced. It's clear that this process is an iterative process. By itself can be very lengthy and generally time and resource consuming. But is this way that, in a systematic way, should ensure really the robustness of the design itself. I want then conclude with a practical example of the use of ISAM. This example actually comes from our Japanese colleagues. Please don't look at the technical detail, but rather on the use of the different tools. So the reference design is the Japanese sodium fast reactor, is loop type SFR, and in terms of decay heat removal system, it has two primary reactor auxiliary cooling systems, so-called PRACs, that are linked with the intermediate heat exchangers, and one direct reactor auxiliary cooling system, also called DRAX, which is directly immersed into the reactor vessel. So the first activity was really to identify the different challenges and mechanisms and through the OPT, really identify the set of provisions to be put in place in order to cope with this mechanism. This is an example developed for the level 3 or for the core heat removal in terms of fundamental safety function. Then the analysis was focusing on the protected loss of heat sink, considering here we are in design extension conditions, so with the failure of one of the tracks. So the exercise wanted to assess the short-term potential loss of cooling, and to assess the capability of keeping the integrity of the core using the remaining tracks and drags, or both of them or either one of them. So the scenario analyzed by the deterministic study was identify the PSA through an event tree, PSA analysis that gave the success of the failure within the 24 hours. So the scenarios were identified and assessed through the DPA that showed that essentially only in case of operational of both the tracks and drags, the core integrity could be guaranteed, while for all the other cases, this will lead to damage. In particular, the initial design for the PSA results related to the protected loss of heat sink showed a core damage frequency of 5 to 10 to the -7 for reactor here, with a heavy contribution of the short term, so of the sequences that occur within the 24 hours after reactor shutdown. In order to improve these values, an option was to enhance the heat removal capacity of a single train within the 24 hours through the addition of non-safety related air-cooled blowers with associated short-term batteries. In this way, from the initial design with the application of these non-safety related air cooler blowers, it was possible to add additional success paths that eventually led to a reduction for the protected loss of heat sink to 9 to 10 to the -9 per reactor here, so about 50 times less than before. This is a very, very, let's say, simple example of how really the combination of OPT for the definition of the provisions and the challenges, and DPA and PSA could indeed help to build in the safety. We reach now the conclusion of this webinar. So, in summary, the Risk and Safety Working Group aims to, let's say, to reach a high level of safety through essentially the combination of the inherent features of the advanced technology with the early application of an improved safety approach. And this is done essentially through a systematic and full and systematic implementation of the defense in depth in such a way that safety is built in rather than added on. As concerns the ISA methodology, we don't have really new tools, but it's really the systematic approach on the use of the methodology that assures a robust demonstration. And the use of ISAM then can indeed support the safety assessment. I want to conclude my webinar with just an overview of the ongoing activities of the Risk and Safety Working Group. In particular, we are working now on the update of the basis, the safety approach for Generation 4 systems. This document was actually produced in 2008. So the idea is really to take into account the lessons learned from Fukushima, as well as the evolution of the regulatory framework in the last 10 years. And then other reports that are done in collaboration with the individual assistance steering committees. To date, we have the white paper related to the pilot application of ISAM methodology. The objective is really to demonstrate the applicability of ISAM as a self-assessment for each of the 6th generation 4 systems, and provide somehow a guidance on improving the safety aspects of the GEMS 4 systems using ISAM. And then the safety assessment reports for the 6th generation 4 systems, that is a kind of a snapshot of the characteristics of these systems, of their challenges, and the remaining R&D needs. And finally, the contribution that the group is giving to the definition of the safety design criteria for the SFR within the dedicated task force, and directly in collaboration with the SSCs for the other designs. Finally, you see here the link, the direct link within the GIF portal to the web page of the Risk and Safety Working Group, where you can find all the documentation developed by the working group in these years. This concludes my webinar, and thank you for your attention. And I'm open to see your questions, answer your questions. Thank you.
Thank you very much, Luca, for your presentation. If you have questions, please feel free to type those into the chat box. While those questions are coming in, we'll just take a quick look at the upcoming webinar presentations. In March, a presentation on the Allegro Experimental Gas-Cooled Fast Reactor Project. In April, we look forward to a European Sodium Fast Reactor and introduction. And in May, the formulation of alternative cement matrix for solidification, stabilization of nuclear waste. Thank you again for your participation. And if you have questions, feel free to type those in now. We have one question. Let me see if I can get that to show for you.
I don't see it.
Actually, it's it's a request to have the presentation provided to one of the attendees, and we will do that following today's presentation. So again, if you have any questions at all, please feel free to type those in, and we'll take as many as we have time for. Luca, there's a question. Are you able to see the question chat box? It says, I was wondering if you could elaborate more on the human factors.
Elaborate more on the human factors.
Right.
Yes. So indeed, I would say this is a good thing related actually to the update that we are doing for the basis approach, because this is somehow linked also to the lesson learned from Fukushima. So in this respect, the safety approach for Generation 4 systems doesn't explicitly include the human factor into the attributes. It's the characteristics of the defense in depth when we talk about, in particular, forgiveness, aim to prepare the design to be able to help somehow any potential intervention of manual intervention in case of accident. So in order to improve somehow the capability of human action in case of accident. This is expressed in terms of the attributes related to that. Any specific assessment of the human factor is clearly to be done eventually in the framework, the probabilistic studies that are associated with the design assessment. But we don't have any specific consideration of that within the design approach. I see there are some questions, but I cannot see them, read them, right?
Does anybody else have questions for the presenter today? Luca has time to take a couple more, I think.
Okay, more human fact. There I see. Oh.
Thank you again, Luca, for taking the time to put this presentation together and share the information with us. It's greatly appreciated. The presentation was recorded today. If you give us just a little bit of time, a couple days, we'll get the recorded version posted to the GIF website where you'll be able to review it at your leisure, along with a copy of the slide deck.
Okay,
yeah,
thank you very much,
everybody. Thank you, Luca.
Thank you, Patricia, also for organizing this.
Have a good day, everybody. Thank you, Berta, again.
Thank you. Bye-bye.
Bye-bye.